Welcome to the Explainer. When you think about plastics or even medicines, have you ever wondered how we actually build those molecules? Well, today we're going to pull back the curtain on that. We're diving into the world of hydrocarbons and the chemical reactions that honestly shape our entire world. Now, I know it might seem like some super complex puzzle, right? But the secret, it's actually in a surprisingly simple playbook. It's all about a set of rules for making and breaking the most basic building blocks of organic chemistry. And those are hydrocarbons. Okay, so let's open up that chemist toolkit. We're going to see exactly how these essential molecules get made and transformed. We're talking about the core reactions that let us build everything from a simple chain all the way up to really intricate rings. All right, first up, let's talk about building the backbone. We're starting with the simplest hydrocarbons out there, alkanes. All these are just chains of single bonded carbon atoms. Honestly, you can think of them as the most basic Lego bricks in the entire organic chemistry set. They form the skeleton for, well, countless other molecules. So, when it comes to making these alkanes, chemists really have two main game plans. On one hand, you can take a molecule that's already got double or triple bonds, what we call unsaturated, and just add hydrogen to fill it all up. That's saturating it. Or you can go a different route, take smaller pieces and literally join them together to build a longer chain from scratch. Okay, let's look at a classic way to build a chain, the Wurtz reaction. This thing is awesome. It's a super powerful way to literally double the length of your carbon chain. You take two identical starting molecules, throw in some sodium metal, and bam, the sodium just rips the halogens off and the two carbon groups link up, creating a brand new bond. But there's a catch, and it's a big one. The Wurtz reaction is fantastic if you want to make a perfectly symmetrical alkane, with an even number of carbons. But what happens if you try to use two different starting pieces? Well, you get a total mess, a mixture of three different products that's just a nightmare to separate. And that is exactly why a chemist's toolkit can't just have one tool. You need the right tool for the right job. So we've built these stable backbones, the alkanes. Now let's create some reactivity. We're moving on to alkenes and alkynes. These guys, with their double and triple bonds, are where the real action is. They are the true powerhouses of organic synthesis. So here's a challenge, right? How do you go from a triple bond down to a double bond without accidentally going all the way to a single bond? You need a catalyst that knows when to stop. And that is exactly what Lindlar's catalyst does. You can think of it as a poisoned catalyst. Its power has been dialed back on purpose, so it just perfectly stops the reaction right at the alkyne stage. Pretty clever, huh? And this is where things get really cool, because it's all about control. We're not just making molecules, we're controlling their exact 3D shape. If you use Lindlar's catalyst, the hydrogens add to the same side of the bond, giving you what's called a cis-alkene. But if you switch to a different reaction, the Birch reduction, the hydrogens add to opposite sides, and that gives you a trans-alkene. It's like having a little molecular switch that lets you decide the final geometry. Absolutely amazing. All right, we've learned how to build these hydrocarbons. Now for the main event. What do they do? How do they react? It turns out their reactions pretty much fall into two very, very different camps: addition versus substitution. And this slide really gets to the heart of it. Think about it this way. Alkanes, the saturated ones, are already holding hands with as many atoms as they can. They're full. So if they want to react, they have to let go of one hand to grab another. That's a substitution. But alkanes and alkenes, they've got these extra bonds, these open connection points. They don't need to swap anything out. They can just break open that extra bond and add new atoms right in. It's a fundamental difference in how they behave. Okay, so when you're adding something like, say, HBr to an alkene that isn't perfectly symmetrical, how do you know where the hydrogen goes and where the bromine goes? Well, there's a famous rule for that, and it's often boiled down to a simple phrase: the rich get richer. And that phrase is the core of Markovnikov's rule. It's actually pretty simple. The hydrogen atom, the H, is going to add to the carbon atom that already has more hydrogens. The rich carbon gets richer in hydrogen. Why? Well, it all comes down to stability. This path creates a more stable intermediate, a little temporary structure called a carbocation. Nature always prefers the most stable path, and that's what we see happening here. But what if you don't want to follow the rules? What if you, as the chemist, need the exact opposite outcome? Well, of course, there's a trick for that. It's a two-step process called hydroboration oxidation, or HBO. This reaction is the ultimate anti-Markovnikov move. It cleverly avoids creating that stable carbocation intermediate, which lets it add the OH group to the less substituted carbon, the one with more hydrogens. It gives chemists complete control. Okay, up until now, we've been talking about chains. But now we get to a really special exception. A whole other class of hydrocarbons, the aromatic compounds. And the undisputed king of all aromatic compounds is benzene. Now you look at benzene and you see all those double bonds and you think, aha, it must react like an alkene, right? It must do addition reactions. But no, benzene is different. It is so incredibly stable. That ring of electrons is like a perfect, impenetrable fortress, and it will do anything to protect that stability. So instead of breaking open the gates for an addition, it just swaps out a guard on the wall. It undergoes substitution to keep that special aromatic ring completely intact. And here is where it gets really strategic. Whatever group is already on the benzene ring acts like a traffic director. It literally tells the next incoming group where it's allowed to attach. We have activating groups that make the ring even more reactive and direct newcomers to the spots right next door or directly across, the ortho and para positions. Then you have deactivating groups that make the ring less reactive and send new groups to the meta positions. This kind of predictability, it's a chemist's dream. It's like having a blueprint for building complex molecules. Okay, so we've gone through this whole chemical toolkit, words, Markovnikov, benzene. But why does any of this matter? What's the point? Well, it's because these reactions, these fundamental steps, aren't just things that happen in a lab flask. They are literally used to build the world that you and I live in every single day. This is where the rubber really meets the road. All of this chemistry matters immensely in our everyday lives. Think about polymerization. That sounds complicated, but it's really just that simple addition reaction we talked about with alkenes, just done over and over and over again. You link up tons of simple little ethene molecules, and what do you get? Polythene. Yeah, the plastic that's used to make bags, bottles, toys, you name it. It all comes from these basic reactions. So that leaves us with this final big question. Just imagine, what new molecules could we design? What huge problems could we solve if we had perfect 100% control over every single one of these reactions? That is the question that drives chemistry forward today. It's what pushes the boundaries of medicine and material science. It all starts right here with this fundamental toolkit. Thanks so much for watching The Explainer.